So, our gracious host may have slightly sexed up the dossier for this symposium. I would say rather than cast doubt on, so Stephen yesterday alerted me to the little blurb that's in the program regarding the symposium, where it's written that, well, let's see, he says it's findings, what is it? Recent results cast doubt on the interpretation of previous results. So anyway, I'd like to argue that, if anything, recent ideas have validated the importance of equivalent noise as a paradigm for studying certain visual processes. The process in particular that I think recent research has validated is the importance of the equivalent noise paradigm for studying the computation of visual statistics. And this page from a Psych Review article in 1954 by Fred Etney, it contains a large, relatively large square full of binary visual noise. And he argued that the left half of this figure looks pretty similar to the right half of this figure. And this, he wrote, demonstrates that when some portion of the visual field contains a quantity of information grossly in excess of the observer's perceptual capacity, he treats those components of information as a statistician treats error variance, averaging out particulars and abstracting certain statistical homogeneities. And so Atney's binary texture was one thing, but the visual system seems to be capable of abstracting all sorts of statistical homogeneities. And in 2001, Dan Ariely suggested that the visual system could compute average size. Same year, my co-author, Stephen Dakin, suggested that the visual system could compute average orientation. I too would like to know I would like to know how the visual system computes these statistics, but as a first step, I focused on the somewhat narrower question of how well the visual system computes these statistics. Time permitting, I'll come back to size, but for now, I'm going to use Stephen's task as an example. So, Stephen's observers were asked to make a judgment regarding the average orientation in a set of before patterns like this. They were asked to judge whether the average orientation was clockwise or anti-clockwise or vertical. And his observers weren't perfect. And I'm fairly confident that they weren't perfect in several ways. I can say that because I was one of them. One obvious source of imperfection is inefficiency. So an inefficient observer may base his judgments on the median orientation instead of the mean. He may use the mode if there is one. He may judge the mean orientation, but not of all gabors. In other words, the inefficient observer makes the wrong calculation. A different kind of imperfection is imprecision. So the imprecise observer may indeed calculate the mean of all orientations, but like virtually all measurements, there will be some variability in his calculation, and he won't get the same value every time. So we saw, I should speed through this because Remy talked about it a little bit. This is, okay, but for those that have just walked in, equivalent noise is the name of the paradigm for disentangling inefficiency from imprecision. And they can be segregated using measurements of threshold. The psychometric function here shows how the mean of the distribution from which these orientations have been drawn affects the observer's probability of reporting responding clockwise or anti-clockwise. And these probabilities are well described by normal distribution. The threshold is the name we give to the standard deviation of that distribution. You can think of the threshold as the just noticeable difference in expected tilt. So to assess both efficiency and precision, we need at least two measurements of threshold, one in low noise and one in high noise. In this context, I'm using the word noise, for Stan's benefit, to describe the standard deviation of orientations in the stimulus. not content with just 2 measurements, Stephen made 7. The dashed line in this figure shows what we would expect from the ideal observer whose decisions are based on the sample mean of 16 Gabor patterns like this. The solid curve shows the behavior of a model observer, and the equation for that model observer is shown here. This particular observer had an efficiency of 38%. Its decisions were based on the sample mean of 6 randomly selected Gabors. And the orientation of each of those Gabors was not measured perfectly. It was independently perturbed by a Gaussian process whose standard deviation is called early noise in this equation. Okay, here's another solid curve which shows the behavior of a different model observer. It too uses only 6 of the 16 Gabors, and their apparent orientations are also perturbed by a Gaussian process. But this time, the perturbations are perfectly correlated. It's as though the whole stimulus has been tilted by a random amount, rather than each individual Gabor. The standard deviation of that Gaussian process is called late noise in this equation. So, if it isn't obvious from the equations, I hope to convince you that the 2 curves are the same. And you may wonder whether it's better to think about equivalent noise as an independent perturbation of each Gabor, or as a single perturbation of the whole stimulus. Or maybe it's better to suppose there's a little of both. But if there's one message I want you to take home from my talk, is that it doesn't really matter. Early noise and late noise both become negligible when the stimulus noise is large. And it's precisely these conditions, when the stimulus noise is large, that we can constrain this parameter called efficiency. And this is the parameter that tells us something about how well observers can calculate summary statistics. So the cognoscenti in the audience will appreciate that there are other things that are also called efficiency. So in a series of papers on this topic, which Remy highlighted, Dennis Pelly has worked to disambiguate these various meanings. So what I'm calling efficiency, he might call calculation efficiency or sampling efficiency. In a relatively recent paper with Bart Farrell, he suggested the term high noise efficiency because it correctly implies that this important type of efficiency can be reliably measured only in high levels of stimulus noise. So, obviously I realize this is a symposium about noise. I'm not going to stand here and tell you that the topic of this symposium doesn't really matter. So, let's consider how we might ascertain whether it would be better to think about the noise that limits the precision of visual statistics as early or late or maybe a little of both. In a 2010 JOV paper, I proposed a way of doing this. My proposal was based on the notion, more of an assumption, that it might be possible to alter the number of Gabors on the screen without altering the precision with which their orientations might be measured. Whether this was a reasonable assumption or not, I don't know. But eliminating crowding certainly doesn't make it any less reasonable. So that's what I did. I also changed the task so that it became 2-interval force choice. You know, I'm going to skip this slide. Trust me, I eliminated crowding. So there's a 3-step procedure that I used to attempt to ascertain whether it was better to think about noise as early or late. Eliminating crowding was step 1. Step 2 is I became agnostic, not with respect to any supernatural power, but with respect to the conceptualization of equivalent noise. It might be early, it might be late. Let's not deny the possibility of either, at least not yet. So accordingly, I formulated this general equation that has both sources of noise. If you prefer, here's an alternative formulation of the same equation, which has only noise, it has a correlation of rho between any two gabors, but it's the same equation. So step 3 of my proposal is, well, it's just what you see here. I varied the size of each array between 1 and 8 Gabor patterns, and asked observers, again using this 2-interval forced choice business, to compare the mean orientations. In these graphs, the numerical symbols in each panel indicate the set size. The solid blue and lavender curves here, they represent fits of my agnostic model to the data for set sizes of 1 and 8 Gabor patterns, respectively. The dash curves, they represent the fit of the same model, but the efficiency parameter was constrained to be 100%. And if you look at the dash lavender curves, they don't fit the data as well as the solid lavender curves. They don't fit the 8s as well. And so we can infer that efficiency must be less than 100%. And you can use a similar logic to infer that the early noise must be greater than 0 for all 4 observers. And for this observer here, you can infer that the late noise must be greater than 0. And this late noise manifests in these curves by the separation between the blue curve representing performance for 1 Gabor and the lavender curve representing performance for 8. They come together down here in low noise. The separation in low noise is less than high noise. There's less of a set size effect in low noise than high noise. And Allard and Kavanaugh recently offered a novel explanation for the same phenomenon. And Raymond talked about this. First, I should mention that this figure of theirs from their paper shows the phenomenon quite clearly. There's no set size effect in, actually it's not low noise, it's no noise, and there's a relatively large set size effect in high external noise. So I just want to reiterate that I don't think this result casts doubt on anything. It fits comfortably within the standard agnostic model of equivalent noise. However, the suggestion that there are perceptually identical orientations, I'm sorry, that was Raymond's suggestion, that when all the orientations appear to be the same, that observers don't average, they just select one. So this suggestion that there are perceptually identical orientations, it does cast doubt on the notion that precision is limited by noise. And I think it's a very interesting idea. Indeed, I think it's so interesting that I wrote 3 papers on the subject. And this figure comes from the middle paper. The first one was with Michael Morgan and Charlie Chubb. This figure comes from the second one. And the question was, if there were perceptually identical orientations, that is, there was a barrier, some barrier in the visual system that prevented us from seeing very small misalignments, how would that manifest in data? And one way, the way we tested it, was to ask observers to compare patterns of almost parallel orientations and ask them which one is more or less parallel. So it's, again, 2 alternative forced choice. So if there were this barrier that prevented us from noticing slight misalignments, then when the pattern was slightly less aligned than that, it should be really easy to detect. And that would manifest as a dip away from this smooth curve that's plotting the pedestal misalignment to the just noticeable difference in its orientation variance. That's what we're measuring. Now, I didn't find very compelling evidence for a barrier like this, but I never considered how such a barrier might manifest in traditional measures of equivalent noise. So let's see. So Stephen collected a whole bunch of data using a task very similar to the one that Raymond presented earlier. For each observer, the blue points represent performances in an experiment where there were 4 Gabor patterns. blue points 1 Gabor pattern, lavender points 4 Gabor patterns. You had to say whether the mean was clockwise or anti-clockwise or vertical. And the dashed curves, they represent fits of my agnostic model to the data. The solid curves represent the fit of an even more agnostic model, that it allows for the possibility of a barrier. So below the barrier, here in low noise, observers just use one of the Gabors, even if there are 4 available. And what happens is, in that case, the 2 curves, the solid curve for blue, the solid curve for lavender, they come together at the low end. Way above the barrier, in high noise, the solid blue and lavender curves there, they match the dashed ones. That is, it's just as though there were no barrier. And then in the middle, there's a region of transition, and you can sort of see this in PB's data, and maybe one other data set, MST here. But I have to say that we have nowhere near enough data to either reject the notion of a barrier for all observers or to accept the notion that there is this significant transitory region. I mean, there may be some overfitting here. So, for example, you know, like here for this particular subject, and we'll do, if time permitting, we'll come back to him. No, out of time. Okay. So I'm gonna wrap up. I'm going to fast forward all of this stuff. Most people will effectively use roughly half of the stimuli that are there, and go straight to my conclusion slide. Okay. So actually, Nagaraja is usually credited with introducing equivalent noise to the field. And you can think, and it's a paradigm for segregating imprecision from inefficiency. And you can think of imprecision as the visual system's measurement error, while inefficiency is more like the visual system making the wrong measurement. Janusz Kulikowski, by the way, is the one who started using the word barrier, which I've been using in these previous slides. But it's a much older idea. And he used it to describe the contrast below which all other contrasts appear identical. And while our field as a whole may have reached a consensus regarding a barrier for contrast, the possibility of a barrier for orientation differences may still deserve further investigation. Ultimately, however, if you want to know something about how statistics like mean orientation can be computed, it's efficiency that you want to calculate. Imprecision is just a distraction, and efficiency doesn't change when you add a barrier. So right now I don't have a very good idea regarding the extent to which estimates of average depend upon the feature of interest, whether it be size or orientation, the display duration, that's all the slides I skipped, or indeed the psychophysical paradigm, whether it's method of classification or 2AFC or whatever. But that's the direction my research is going. Thank you for listening to me. Thanks for the invitation.
Okay, thank you, Josh. We are still running a bit behind schedule, so if we can get Peter up for the next talk. If anyone has a very quick question, just want Peter to set it up. Please go ahead. Okay, you want to go to the microphone?
Very nice talk. Thanks a lot. I've got one quick question.
Sure.
You did all the measurements with orientation, which lends itself to those measurements because you have a very simple decision between leftward, rightward, and vertical. Would you deem necessary to include other features like spatial frequency or color or size, which you obviously did to validate your argument?
Yes, that's an excellent question. So first I should just clarify one thing, is that when I do the experiment, it's always 2AFC because I am concerned that when vertical is the reference, and it's a classification issue, that the response of fixed filters that are tuned just on either side of vertical may act as a proxy for calculations of the mean. I mean, somehow we have to calculate the mean, but I just want to make it more difficult than that. So it's 2AFC, and the first interval has a random mean, and the second interval is just like because there's no, particularly if you average across all random orientations, such subtleties as the oblique effect, the various, the mapping of stimulus intensity to perceived intensity, it doesn't become an issue. You can sort of skate over all of those difficulties. But the other dimensions are of interest, and we can talk about them later. It's Peter's turn. Thanks for the question.
Hey, thank you, Josh.